who comes to us indirectly from the Hebrew University of Jerusalem. He did his PhD originally in physics in Jerusalem, and then spent time in a number of places, notably Bell Labs, where he spent a long stint and overlapped with David, and also at Santa Barbara, and he's just been doing a sabbatical at Penn, and in fact returns home tomorrow. So we're very grateful that he's agreed to spend like his last day here with us. So Tali is I think of him basically as a machine learning guy who's worked on a number of different areas, including, many of you know his paper on distributional clustering of English words, and a number of follow-up papers to that. But he's also worked on a number of other problems, including, as you can see from his affiliations, neural activity, for example, neural spike trains, cortical activity, musical sounds, cursive handwriting, and so forth, in addition to words and documents. And a thread that really runs through a lot of his work is this idea of smoothing. So you'd like to be able to find a lower dimensional description of high dimensional data that gives up as little as possible, which is a perspective that he tells me he was exposed to from being trained originally in statistical mechanics, where you'd like to be able to describe a glass of water, for example, in macroscopically, despite the fact that you have all these little atoms bouncing around under the hood. You can give a very accurate low-dimensional description in terms of properties like temperature and entropy. So I've said quite enough, and let's give him the rest of the hour.
Thank you very much for this introduction. It's really a pleasure to be here. So you've been managed to. Oh, hi. I see some familiar faces again. Maybe not. I'm here since 10 in the morning, and essentially getting no moment of rest since then. By the time of the talk, I'm a bit exhausted. What I want to tell you about is really some sort of mid-term report of a very long project that started maybe 15 years ago with people like Al and Fernando Pereira and others at Bell Labs, and really has to do with what is it in language, in particular, and in complex systems, complex data in general, that allow us to make sense of it in some meaningful way. And has been developed quite nicely recently, and it really started, and very much my talk is about what can we learn from co-occurrence statistics. That's usually the way I like to think about it. So imagine that you are given joint counts of words in documents. This is something simple enough that everyone can appreciate. So imagine that, I don't know, you're given documents, and the first document has something like 12 times the word audio, and the third document 20 times the word doctor, and so on. My talk is very much about not only what can you do with it practically, which is interesting and maybe even useful, and like clustering, classifying documents and sending your right email to the right place and so on, which is things that I've been involved in, but it's not really the topic here. But what can you learn anything really more profound, more fundamental about language in general, and about the way words are generated and acquired in human language? So I'm talking here about the science. I guess I should say it once, start looking at this camera. Anyway, so remember this example, I'll come to it later on in the talk. What is it that you can learn from co-occurrence statistics? And I'm going to take you through a very long and I hope interesting detour, trying to convey some of the basic ideas that influenced me and the work that I've been doing with many other people recently. So when we talk about language as actually all of science, if you want, we are really talking about something which I call the fundamental dilemma, which is how do you trade complexity with accuracy? in some sense. I mean, so we are all used to think about simple models like fitting straight lines through points or things like this, which are where the problem doesn't really come up in its full beauty, but real data coming from real difficult problems, whether they are linguistic or neuroscience or computational biology or whatever today, has some peculiar property that the more you see, the more you can say about the model, and the more data you are given, the more complex your models become. And that's something which really bugs me for many, many years, especially when people talk about, this is the correct model of my data, which is obviously a ridiculous statement in most cases, unless your data really comes from, as I said, some toy problem. So I'm going to spend a few minutes talking about what I call this fundamental dilemma. What is it that we actually learn by fitting models to data? And what can we say about the right level of description of data, which is interesting. Then I'm going to take you through an analogy which I do with actually statistical physics and its cousin, information theory, which is really formulating this as some sort of optimization problem, as a trade-off between different things, between competing desires. And that's the way we usually like to I mean, I think that the most successful example of it is really statistical physics, but it's all about trade-offs. And when you realize that, you see that there is really, you can formulate this basic dilemma of complexity and accuracy in terms of very natural trade-offs. And this is how I get into all sorts of variational principles. This actually, I think, is the wrong slide here. Never mind. And then I'm going to apply it. I'm actually going to argue that if you think about it in Shannon's way, and really see what Shannon did in his information theory, you see that it's all about trading distortion with cost in some sense. But this distortion and cost in communication can be turned inside out, if you want, into trading values of future information. And that's the lesson I want to give you in the central part of the talk. And this leads to some sort of an interesting variational principle, which I call the information bottleneck. Some other people are starting to use this name as well, so not only my students, but it's probably catching up more or less. And then I'll come back to this document analysis, the language problem, and try to convince you that using this type of analysis on language, you can learn something new about language, in particular the way information, or what meaningful information, scales with the complexity of the language. And that's going to be the interesting application here. And this usually brings me way beyond my time. So what is this fundamental dilemma? So when we talk about learning theory, we usually have in mind something like fitting functions to given data. So imagine, for example, points on the plan, x, y points. This is your data. Now, what most of you will try to do immediately is to, okay, so this is probably an example of something like this. Some sort of a curve, a function that goes through the data. But of course, when you do that, you make all sorts of assumptions, sometimes not very explicit, about the nature of the noise, for example, the nature of the class of functions that can go there. Do you actually assume part of it? So, of course, I could just as well put something, so I assume some sort of relationship like this, and I assume that the points are not that important if I do this point. But maybe this sounds like a much better fit to the points that actually go exactly through my data, but most of you will not take this green curve much more seriously than the blue one, and you'll be quite right about it, because actually in this case, a straight line you can only do just as good. So what's going on here? What is the process that we are doing when we are fitting curves to data? Because, as I'm sure all of you know, what we really care about is how well this function that we fit through the data fits new data, and actually makes prediction of what we call generalized beyond the given data. So if I give you a new point there, I'll say, that's the new point. So maybe a straight line is not so bad, I don't know. But so essentially what we are actually doing here, we play with different representation of different complexities of our data and compare it to the accuracy that it gives us on new data. So this is this fundamental dilemma that I'm talking about. What is really the mechanism in which we trade accuracy with simplicity or with complexity? Of course, we all know that good models should be able to make good predictions, but there's something more than that. It's really how is accuracy going to improve when I add more and more complexity? This is the question I'm interested in. Actually, the same thing is true. I thought I had another curve. Never mind. So,
can you ask questions now or later? Can you ask questions now?
Sure, ask questions. How long are you? My train is 6:30. That's not.
So how is the dynamic range of the data comes into play here?
Well, it's a very good question. It requires a little more than one sentence of answer. But obviously, this is part of your assumptions, and background knowledge about the data, and it plays a major role. If you actually look at the theory and the nature of those bounds that I actually put on generalization, they always have this dynamic range somewhere, one way or another. And but it's a little technical for this part of it. Okay, so actually I had another slide that somehow I managed to erase on the train, I guess. But it's the same is true about unsupervised learning. If you talk about clustering, for example, you have also the same type of trade-off. I mean, you have clouds of points, and then what is the number of clusters, or what is the? It's of course an arbitrary question. The question is how much do you gain by adding another cluster in terms of accuracy? That's the interesting question. It's not that the number of clusters is 5. That's okay, maybe, but it's really how much do you gain by moving from 4 to 5, and from 5 to 6, from 6 to 7, and really how is this trade-off looks like. So I'm actually interested in some sort of describing quantitatively the connection between complexity and accuracy in general. So far I'm being so vague and so general that what can you tell me about such a quantitative curve? So even without specifying anything about the way I measure complexity and accuracy, if I ask anyone here, what do you expect to see in this curve? I'm sure that all of you will agree that 0 complexity should give me 0 accuracy. When, if I don't invest anything in my description, I will probably not get much accuracy beyond, some trivialities. So the origin should be there. And of course, you also know that if I increase complexity, and remember, I'm not talking about the true accuracy beyond my training data, I should improve accuracy in the sense that if I'm allowing a certain complexity, all the least complex models are also possible, okay? Of course, I can always waste my bits, my complexity measure. So you expect something of that nature, that's my claim. So you expect to start more or less linearly. Actually, I can prove it's linearly if you measure it correctly, with some very important, interesting slope at the beginning. But then, at some point, adding complexity is not going to add too much to your accuracy, and where you exhaust the complexity of your phenomenon. So in some sense, you're going to give me more and more complex data. Remember, talking about generalization error here, in some sense, this is not entirely true, but you reach a point of what we call diminishing return. You add more complexity and you don't get much more accuracy for that. So you're going to saturate at some point. If you're talking about finite problems.
It never gets worse.
Oh, okay. So of course, I was cheating a little bit. So there's one interesting, so first of all, in order to define it properly, I define this line as the limit, the most accurate model that can achieve at a given certain complexity. So it's a very nice optimization problem. You specify its complexity. This blue curve is the accuracy of the most accurate model that you can achieve at that level of complexity. Okay, so that defines it more or less. Anything below this is achievable, is possible. Anything above it is inachievable or impossible, and this is the boundary. Still, didn't quite define the problem, but it's getting there. And of course, as was mentioned here, there's one problem with real life. Real data, we always have finite data. Unfortunately, we never have all the data that we want. So if we have limited data, what do you expect to happen? Imagine that I don't really have everything about the problem. So I usually expect something like this, which is very simple models I can probably estimate well enough. And I actually want to claim that I can estimate them almost as good as I can do with the full set of data, especially if my model are really, really simple. But now when I try to estimate or get better models than my data allows me, I see this very nice maximum of peaking, which some people call overfitting. Essentially, getting your complexity beyond what the data allows you is going to deteriorate your performance or your accuracy. So this is the classical overfitting phenomenon. I'm not going to talk about it today. This is really the essential, one of the key questions in machine learning, how to estimate the distance, the deviation between this blue and green curves. And there's been very nice work recently in the context of what I'm talking about, estimating this deviation, where is this the point that you have to stop as a function of your sample size. But that's, for me, that's more or less a solved issue, although we know how to handle this. We know how to control the complexity. The interesting question is really, what is the nature of this curve in general? There's another caveat, which is the issue of bounded computation. Imagine that I don't really have all the computing power in the world. Unfortunately, although sometimes it's true. So, and in this case, you may not be able to solve this optimization problem. There's simply no way I can give you data which is so complex that in order to actually find a good description of it, you have to solve some hard problems which are beyond your power. So in this case, you in general expect that your bounded computation will reduce this trade-off significantly. Actually, I claim that the trivial endpoints are usually very easy to compute, but anything in between may not be accessible. So keeping those two reservation caveats in mind, I'm going to run as if I have all the data and all the computer power in the world. Okay. Now, just to make sure that you know that my motivation is also about biology. So this type of trade-off, I mean, complexity versus accuracy, is really behind everything around us in some very profound way. Especially, it's behind living organisms. I mean, they have to trade to other things, which are efficiency and survivability, which are directly linked to this. But this is about all I want to say right now about biology. So how can we quantify it? So it turns out that accuracy is usually measured by some sort of an average distortion. So if I give you, let's say, the square error in the case of this curve regression problem, and then, of course, you know how to measure accuracy. If you have a distortion measure, okay, if you have a distortion measure that you trust. And simplicity or complexity is usually measured, at least with computer scientists, I don't have to argue too much for that, by some sort of number of bits that describe our models, okay? It has a very long history of very good people who contributed to this idea, but buy it now. So I'm going to measure complexity by average distortion and accuracy by average number of bits, minimum number of bits that require to describe my model, which is, of course, a very hard problem in general. But imagine that you buy this, then, of course, what I'm looking for is some sort of a trade-off between distortion and compression. If I'm looking for trade-off between compression, unfortunately or fortunately, this problem has been solved more or less satisfactorily within information theory and within Shannon theory. This is one of the key questions that something about the rate distortion theory. So excuse me, those many experts in information theory here in the audience. I'm going to introduce information theory very briefly. And I do it very quickly because I'm really behind schedule. So Shannon theory is about sending messages between one end to another end, between a source and the receiver. And of course, this source is characterized by some sort of statistics, so distribution over messages, over possible messages. And in order to do this, you need to communicate through some sort of a channel. And this channel is usually a physical entity, like the air between us now, or something like this, which actually can be modulated, can be in some interesting and complicated way. But Shannon really had this great insight that every channel, even continuous channels like the air between us, or the radio waves, or whatever it is, has to be quantized in some very fundamental sense. So I can always think about channels quantized into symbols, which are distinguishable in some, let's say, energy, frequency, time sense, or some whatever. Now, so without without losing anything. I can think about those symbols as bits. Now, here's the problem. I have messages which are those vague ideas that I have in my head right now, and I'm trying to send them and create some sort of a distorted image of them in your brain through this very noisy channel in between us. So of course, in order to do this, I need some sort of an encoding and decoding process in between us that will translate the messages into the symbols of the channel. So far, everything is known as and clear, I hope. But now came another great insight of Shannon, that you can break this encoding decoding problem, of course, for it to be meaningful. It's actually separable into two different problems. One of them is source coding, which has to do with eliminating redundancies in the source. So I want to remove all those things that I can, compress the source as much as I can. This is since then known as source coding. And the other one is known as channel coding, which has to do with correcting possible errors due to noise in the channel. So it's actually very interesting symmetry between those problems. One of them has to do with eliminating redundancies, the other one has to do with adding redundancies such that I can compensate for the errors and for the noise in the channel. Actually, since this separation lemma or theorem of Shannon, information theory made it through a bifurcation more or less, and there were people who were dealing with source coding and other people who were dealing with channel coding, and they hardly talk to each other. Not quite, but it turns out that you're going to separate them. So correct the errors in the channel first, make it noiseless. As I wanted to say, any channel, of course, has noise, which means that the symbols at the input are not necessarily the symbols at the output, but they're related to them somehow, so statistically. And once you correct the channel in the source, the noise in the channel, then of course you can solve the source coding problem independently. And as I said, a lot of clever people spent years of their life finding very good and very sophisticated method of doing channel coding, which is error correction coding, and doing compression with or without losses. All right? Now it turns out that this was a great insight, but it introduced also some interesting problems into information theory, in particular the notion of long delays and long blocks, because the whole thing of correcting the noise has to deal with, can be done only asymptotically in some sense. So now once you introduce long delays and long blocks, the whole thing, the notion of time, for example, is lost. When you can't really say when is it that if I have to send you the message within the next 2 seconds, then I cannot use infinitely long blocks. Anyway, this is compression, this is error correction. One of them involves something like the source entropy, the other one involves channel capacity. I really have to, and it's very important to realize that what most of us really learn in first course in information theory, where you talk about lossless compression and channels with no constraints, are just only the end points in some sense of a full picture, which emerge only when you consider lossy compression, distortions, and consider cost on the channel. So essentially, this compression problem is part of something which is known as rate distortion theory. And the capacity problem, the maximum reconstructible bits at the end of the channel, is actually part of a larger problem known as the capacity cost or capacity efficiency problem. I'm sure all of you know that. Now, what Shannon realized is that actually historically it happens in a very different way. So I think it's a very confusing issue. Historically, the whole thing went from cryptography, if you really want to know. I mean, this whole notion of separation really comes from Shannon's thinking about cryptography during the war, and where is the best place to put a cryptographic system, which is, of course, after the compression, before the error correction. But people forgot about it. And it's also only later, not in the 48 paper, but in the 56 and then 59 papers on rate distortion, of course, where the whole picture of distortion and the full picture really emerged. And in many ways, I think essentially all the books on information theory follow this traditional bottom-up construction of Shannon from axioms about entropy and so on. And rarely they tell you the whole picture, which is really, if you tell it, sometimes towards the end of the book, that it's really about distortion, efficiency, trade-off, distortion, cost trade-off. That's what it is. And what Shannon managed to tell us that in order to solve this problem, you really need to think about something else, which is information at the entry to the channel. So why information? So there's something about measuring information. I'm sure all of you know that. Again, I'm skipping all sorts of slides here, but never mind. Information comes when you have to think about representation of a variable x. And I'm sorry if I'm getting a little more technical here. So imagine x, which is my input variable, which has some sort of statistical behavior, and by this blue blob, I actually mean all the possible realization of x. And now I want to represent it with a smaller variable, a simpler variable. So what a typical picture information theory tells us, okay, you want to stochastically represent x by x hat. What you need to do for that is to find some sort of a stochastic map, a conditional distribution that tells you what is x hat for a given x. This is your problem. And now, this is it means that some of those green blob area has to be mapped into one point. So I'm going to lose the distinctions that were in my original variable and represent all of them by one point, at least statistically. And in order to make this representation faithful enough within the size of the blobs, I really have to think about the sizes of these two things. So here comes this famous entropy measure, which is really not what I'm interested in, but the size of this block x is exponential with something known as the entropy, which is simply just counting it. How many realizations of long sequences of x are there, where n is the size of the sequence? And this is 2 to the nh. The size of this green blob is also exponential in something else, which is known as the conditional entropy, when I know this map. Now the question is, how many bits do I need in order to represent my x by this particular map x hat? And the answer is exactly the number of green blobs that I can pack without overlap in the blue blob. How much is this? Precisely the ratio of these two things. And this ratio is giving me what people know as the mutual information, which is really the number of bits needed to specify a blob in this representation. So that's essentially why mutual information appears. It's a very hand-waving type of argument. Mutual information is important not because it's a good measure of independence, as most people think, and not because it is I don't know, a nice symmetric function of the variables, but because it counts typical sequences in some very interesting way, and it really tells me what are the number of possible realization of the two variables that actually captures the dependence between them. It's really a counting argument among anything else. Now, once I have mutual information, Shannon showed us that these two problems, the rate distortion, how do I trade the distortion between the ends, and the side of the representation and the input to the channel, and the other problem, the capacity efficiency problem, both of them can be formulated through mutual information. I'm sorry if I'm butchering information theory now, but what can I do in 1 hour? So essentially, Shannon told us something very remarkable. The first problem, which is how the source coding problem, how to eliminate the redundancies, boils down to one expression. Minimize the mutual information between your input and your representation side, subject to whatever it is that you want to preserve in terms of distortion. Okay? So subject to a distortion constraint. So this is essentially known as the rate distortion function, and I'll say something about this function in a second. The other problem, which is the channel coding, how much is it that I'm willing to transfer through the channel such that I can represent faithfully, I mean, this is the maximum number of bits that can be reliably predicted across the channel. Remember, the source coding has to deal with past, compressing things that I already saw, and the channel coding has to deal with future, and trying to improve my prediction across an unknown channel. I don't know which bits are going to be twisted during the channel, in the channel. So this has to deal with maximizing information, and this defines these two functions. What is the best compression you can achieve at the given distortion level, the rate distortion function, R of D, and what is the maximum bits that you can reliably reconstruct on the other side, which is called the capacity cost trade-off. Imagine that there's some cost in between. The interesting thing about it is now that the cost distortion relationship, which is the external form of the communication, is turned into matching two values of information. The compression versus prediction. One of them has to deal with maximizing information, the other one is minimizing information. I know I'm skipping all sorts of details here, but excuse me. So anyway, the solution to this problem is actually technical and very simple in a sense. It has to do with finding those optimal trade-offs, given the distortion function, the rate distortion function usually has this convex behavior. It's always starting with the entropy, which is the lossless compression, and goes down to 0 when you allow the maximum possible compression, maximum possible distortion, and this curve again separates these two possible phases, and the slope is not constant. Actually, it tells you how much accuracy you gain by adding another bit to your representation. And the other problem, which is maximizing information, has a solution of that nature, very much like the function that I started with. This is how many bits you are able to reliably reconstruct on the other side of the channel as a function of the cost of the representation in the channel, the power, the number of bits, or whatever it is. And this goes up like this concave function. And the way these two things, again here, the slope is not constant, it saturates at some point. It tells you how many bits in the representation you get per unit of cost, let's say energy. Okay. Now these two problems are really dual in the sense that you really work with them together as an engineer. Let's say when you are designing a communication system, like a cellular telephone, what you are given is a channel, a cost, and a distortion which is acceptable for your clients. They are willing to pay for that. And then you start with the distortion, you calculate the distortion function, you calculate the minimum rate that you need for this distortion. Then you go to your channel and say, this is the minimum capacity of the channel that I need, and this is going to be the cost that is going to cost. This gives you again the DE, the cost rate, the cost distortion rate. Two of them together. This is the best you can achieve. So essentially what Shannon showed us is that the cost distortion trade-off can be decomposed into two functions which involve mutual information, one by maximization, the other by minimization. And when they are matched together, you have optimal systems. Okay, so that's information theory. Interestingly enough, for some cases, like Gaussian channels, for example, these two problems are well known and analytically solvable. And you know, Gaussian channel, I mean, I'm sure you know what it is, that the source is a Gaussian variable with some standard deviation, and the channel is also a Gaussian channel with the conditional distribution is conditionally Gaussian, and so on. And this is the capacity cost, it's the log of the signal to noise ratio, if you want, 1 plus the signal to noise ratio, and this is the distortion function. Now, when they are matched, which means that this R of D equals C of E, there's a nice, very simple relationship between the distortion and the cost. But what is really more remarkable, that you can achieve it with no coding at all. Which means just send your scaled Gaussian variable through the channel, and the noise in the channel is going to be precisely what your distortion allows. Which is some sort of a no coding problem, no coding theorem. It turns out to be more general than that. It happens in many, many other cases. Remember that? I'll come back to this. So in some cases, solving these problems together is easier than solving each one of them separately, much easier. And biology has a lot to do with that. Oh my God. So I'm about 1/4 of my talk, about 2/3 of the time. Anyway, this is a nice quotation taken from Shannon 1959 paper, which I always like to bring because it shows the insight of this man, and unfortunately this quote is really ignored in many cases. So he actually told you what I just told you. You can read it. That these two problems are dual to each other, and this is he called it provocative and intriguing, curious problem that this cost capacity and the rate distortion are dual to each other. And then he said that this duality can be pursued further, and there's related duality between past and future and the notion of control and knowledge. Thus, we may have knowledge of the past and cannot control it, but we may control the future but have no knowledge of it. Besides being a very poetic sentence, it's actually a very inspiring, I must say, at least for me, because this is precisely what I want to do: merge these two things in a way that looks where the compressive part has to do with the past, and the predictive part, the channel part, has to do with the future. Okay, so how do you do it? So here's this basic idea, which since this is my work, I can say it much faster. So imagine now that the problem is what I sometimes call the inverse Shannon problem. I am having a black box, as many of us have. Like, for example, I have two stations in my auditory pathway that I'm measuring, and something very complicated happens in between. And so I have these 2 points, x and y, and I'm measuring the statistics of the input and the output of my box. And now, what can you tell me from this input-output statistics about the inside of the box? This is the system identification problem, but it's in a very general sense a system identification problem. So imagine that these 2 points, x and y, are not independent. Okay, of course, if what you do with the input doesn't affect the output, look for another problem. but if there is some sort of statistical relationship between them, then it means that if I constrain x, the values of y are going to be restricted, the distribution is going to be affected by that. So in other words, there's mutual information between the 2 variables. Now what I'm actually after is some sort of an explanation. So I'm actually looking for a representation of my input variable x in a way that can explain in the best allowable, achievable way the relationship between x and y. The way you do it, okay, so you look for some sort of a stochastic map from x to x hat, just as we did before. But at this point, I want to constrain it not by a distortion measure, but the amount of information that this representation of x provides me about y. So there's another unknown distribution here, which is how much y is related to this hidden representation. So that's a very nice symmetric picture. You compress, and then you predict. One has to do with the source coding problem, the other one has to do with the channel coding problem. But the nice thing about it is when you put them together, they balance each other. You don't need a distortion and cost anymore. So there are 2 values of mutual information here. One is how much information you preserved about the past, about x. And the other one is how much information this representation is going to allow you about the future, y. I want to control them. I want to balance them together. So there's those 3 unknown distributions that I have to get out of my principle. How x hat is related to x, how y is related to x hat, and what is the prior on x hat. Now it turns out that this problem is very self-balanced, and it actually turns out to be very common. This is one example that I always like to show when I talk to neuroscientists. Neural networks, for example, people have been thinking about this type of representation, where you actually squeeze an input-output relation and then training with backpropagation, things like this, where the hidden layer is smaller, and you're trying to make it as small as possible, such that it captures, it's still able to do the right mapping, and then this hidden layer is actually able to capture some interesting features about the input with respect to the output. And this has been done a long time ago, and then they called it bottleneck, and I thought, okay, that's a nice name. It's a bottleneck of in this case, representation. So it's a good name to call it an information bottleneck because I'm squeezing information. And of course, this can be done with past and future between 2 samples and many other things. Now let me run out through the details here. Once you know what you want to do, so I want to trade these 2 values of information. I want to solve the source and channel coding problems together such that they control each other. The whole thing is just to write, it's just mathematics. So I'm looking for the best compression of x such that it makes good prediction of y. I can write it by introducing a Lagrange multiplier that take care of this compression. How much is it that you want? How much you want to pay for a bit of compression versus a bit of prediction? The trade between these 2 things is precisely this Lagrange multiplier. Sometimes you care more about prediction, which means that this Lagrange multiplier actually is going to take me from simpler to more complex, and for less accurate to more accurate relationship. And this values of the 2 information is precisely going to be my accuracy complexity trade. So this is my proposal for doing that. Now the nice thing about it is that this problem can be solved analytically in a sense. You can actually take derivatives with respect to an unknown distribution without assuming any class, any parametric class at all, and you get equations which look complicated but actually not so complicated, which reminds any one of you should remind something like a clustering of distributions. And essentially, these 3 equations have to be solved iteratively, together, self-consistently, and it actually yields a very nice algorithm, which is some sort of a generalization of what people know in information theory as the Plato or model algorithm. On one hand, actually related to EM in statistical inference. On the other hand, it's an alternating projection algorithm. It has a nice formulation in terms of information geometry and projections and sets of distributions. But essentially what it has to do is some sort of projection between 3 sets of distributions. iteratively, and we know how to prove it, to prove convergence. And unfortunately, the solution is not unique, but it's always converged to the local optimum of this Lagrangian. What is really nice about it is without assuming anything about the distortion function in this case, there's some natural distortion that emerges from these constraints, which is precisely what you would expect it to be. It's the cross entropy, the KL divergence between my actual prediction of y from x and my prediction through the hidden representation. This is how much my distortion, and how much I distorted, how much I lost by using this representation inside. It's a very natural distortion. Okay, just one more thing. So imagine, actually in the original, some of those ideas emerged already early in '93 with this work that was mentioned earlier with Fernando Pereira and Lilian Leo clustering words. And then I just guessed that this should be the right answer. We didn't have all the nice story about information theory. It turns out that this is really the right answer if what you care about is mutual information. Why you care about mutual information? Because this is the right operational function in terms of controlling your prediction errors in the future and measuring your complexity in the future. So there's not in the past. There's really not much freedom here. Okay, so now I want to go back to my nice matrix of words and word counts. What can I do with this? So believe me, we apply this to anything that moves around. Biology and neuroscience and proteins and documents and whatever, URLs and users, whatever. Anything that had nice, interesting joint statistics that you care about. Why? Because we really want to know, given the statistic, what explains, this is some sort of really a very fundamental data explanatory type of analysis, but I want to talk in particular about language here because, after all, this is a language seminar. So what do I do with those words? So now I can do the following. I want to compress this matrix together such that mutual information between words and documents, or I'll later on talk about topics, not documents, which is somewhat easier to control statistically. So imagine that now I permute this matrix such that I put document 1, 4, and 8 together and so on, and I change the words. And then you see very nice blocks. Of course, this is an artificial example, don't take it seriously. But here you see very nicely that there's a set of documents to talk about audio and another set of documents. Of course, I know this is audio. The algorithm, of course, has absolutely no notion of the audio, but you know it after you look at the words, and then there's another set of documents to talk about health and so on. So essentially what I do here is now I can compress let's say the documents into clusters of documents within which the distinction is not really important in terms of mutual information about the identity of the words. And the same is true about the words. I can do this, believe me, we know how to do it jointly on the two variables, and we do all sorts of funny things. So I can compress this matrix to a 3x3 matrix or something like this, which will contain almost the same mutual information as the original matrix. And this will be some sort of a sufficient statistics in terms of what is it that I need to know about the documents in order to make predictions of the words, or I need to know about the words in order to make predictions about the documents. So those are clusters that preserve what I call the relevant information in terms of words. Of course, if you care about other things, there are different clusters. It's not a correct cluster, it's a clusters with respect to this particular representation of the data. So let me just have a nicer graphics here. So essentially you have this joint co-occurrence statistics, which looks very much like a gene expression data, but it's not. But actually gene expression data have exactly the same type of structure. And you want to look for some sort of permutation that allows you to eliminate the distinction, and you quantify this distinction. So what I call the irrelevant distinctions, in this case, are what happens inside each cluster. They are irrelevant with respect to the identity of the words, of the document. So that's the theory, and you quantify this by mutual information. So now the surprise is that language has entirely different behavior. No, this is what you would imagine that you could do. And now, okay, let's see what happens to those clusters, which is really, by increasing the complexity of my representation, I'm getting more and more information about the uniqueness of words. So this is, by the way, is directly related to the work of my ex-PhD student, Noam Slonim. is currently working for Bill Bialik and doing the same things with neurons and other things. So that's what he had in mind, or we had in mind, try to use those clusters in order to make good document classification categorization problem. It actually solves the problem amazingly well, better than most other methods. You are welcome to look at several of our SIG-IR papers. This is the most critical community that you can imagine in terms of, they don't care about beauty of algorithms, they care about accuracy and performance in the verse. And we managed to beat some systems which really tailor very carefully to this problem. But what I find very interesting, so we took, let's say Noam took a very famous database, which is known as the 20 newsgroup database, which contains 20,000 documents taken from 20 different categories, which are just discussion groups on the internet. So things like Sport USA, politics Middle East, things like this. And then this was collected in Carnegie Mellon by Lang. And now you looked at the word category statistics. So it's simple because you have only 20 categories and you can do the statistics quite well. And what you get there is through some process of increasing this parameter beta slowly, which is really going from low complexity to high complexity, gradually, just by, I'm trying to squeeze more and more relevant information from my data by increasing beta. So beta equals 0 is the origin, and then at some point there's a critical beta which has to do with this positive slope of the curve at the origin, and then beyond that I'm just squeezing more and more information. So this is some sort of deterministic annealing algorithm, although here it seems even more natural to me than in the original context of conditional entropy. But so what you get are clusters. So this is the first split, which happens at the origin at this critical temperature, critical beta, which is where things start to appear in some sense. So you get this very nice split of both categories and words, and you can do it. You repeat this process again and again until you get a full tree of categories versus clusters of words. Now you can look at even more interesting. So, okay, you believe me that those clusters actually make sense. For example, here's one example taken from the real data. Leading words there are things like atheist, Christianity, Jesus, and so on. And the category that goes with it, atheism, religion, and so on. So this is perfectly okay. Of course, there are many other ways of getting this type of analysis. But what is really interesting is that now I can actually plot the complexity-accuracy relationship for English language, at least for this database. By plotting these two measures that I worked so hard to develop for you, one of them is the compressing part of the information, the past, and I normalize it to 1 by dividing it by the entropy of the words. And the other one is how well the words cluster predict my topic. And I normalize this to 1 by dividing it by the total information. So this is going to give me the actual relationship between word complexity versus meaningful information. Now let me quantify this to very loaded descriptors. So essentially what you have there is how much, imagine that I reduce my language, my full vocabulary to only 10 clusters of words. That's it. So I give you a document, and instead of writing the word there, I just write numbers between 1 and 10 if you want colors. And I give you this document, okay, now you tell me how much is left at this reduced description of the language about the topic, of the identity of the topic. As a function, when I increase more and more the number of words in my vocabulary. So it's really, I'm going to talk about something which reminds other things which are essentially trivial, like this law, but it's not. Because I'm really talking about information that preserves about identity of topic, which is the meaningful information, and that's the y-axis here. So what Noam did, he used an algorithm which is some sort of an approximation to his to the true thing to do, which is an agglomerative algorithm, which we call agglomerative IB. And he got, for many different clusters, he got this type of curve.
I'm really surprised this isn't shaped more dramatically like this.
Second,
No, okay.
there's a story to tell him. So so of course this algorithm, I looked at this curve and I said, this is ugly. There must be a better approximation. So together with actually Neil Friedman, they developed an improved version of this algorithm which generates much better clusters. And this much better clusters, the red, this is something which we call SIB, how do you call it? Segmental IB or whatever. Sequential IB. It's one of those papers. Anyway, this gives you something which begins to look like what I want it to be, like improved mathematically. It has to be a concave function which has a very nice derivative everywhere because it's directly related to distortion, rate distortion, and cost capacity problem. So actually I told him, you know what, now that you have the solution, calculate the true bound using the equations of the IB, the alternating iterative, by a process which we call reverse annealing. Because there are all sorts of tricky issues here if you start from the beginning. But if you start from the end, it's actually very easy to do the whole curve. And for this particular problem, that's the curve we got. Which is very nice. It's really the ultimate bound. It tells you what is it that, this gives you essentially the best, if you want. This is I claim if this is the right solution to the problem, since no clusters that we achieved with any of the algorithms seem to go beyond that, so this probably is a bound. So given this representation complexity, which means this is the log of the number of partition averaged, in simpler words, it has to do directly with the number of words and the complexity of representation. Actually, I'll show you exactly the conditional entropy of your reduced language. And this is how much this representation allows you in terms of prediction of the topic. Now, this doesn't look like anything that's saturated at some point. Actually, it's an amazingly smooth curve, which it's actually different from the curve that you've seen before in a very profound way. Now, I looked at this curve and thought, look, this must have an explanation. So of course, like a good physicist, I plotted this curve in a log-log plot. But I plotted it. Of course, it reminded me of a power law for reasons which I'll show in a second. But if you inverse it and then plot it in a log-log plot, you get perfect straight line. This is the real data. Remember, this is a straight line that's coming from this funny collection of documents collected by Lang at Carnegie Mellon. It was not a conspiracy for me, but it's almost a perfect power law. And actually, the slope of this power law happens to be a non-trivial exponent. Believe me, I've been playing with exponents all my life when I used to be a physicist, and critical exponents like this. This is a 1.92, it's not a 2. And this exponent tells you that the remaining information, meaningful information, scales like the remaining information with some power. And what's nice about power laws is that they are, in a very nice sense, self-similar. So let me explain that. Essentially, if I look at some subset of this curve, let's say I went to a reduced description of the language at a given point, whatever, this smaller rectangle, and I plot a log-log plot of this smaller curve, I'll get exactly the same exponent. Okay? Because you all know that. Power laws are defined by the relationship between the slope and the derivative and the slope of the string here. So essentially, here's a cleaner picture of the same thing. This is my best accuracy complexity relationship for English language, if you want. Essentially, what's plotted here is on this side is the conditional entropy of the words given my representation, because it's h minus the information, and it's entropy. So this is precisely the conditional. It's a good measure as any other of the complexity of my language at some point, at the given vocabulary size, because I'm actually using the words in a non-uniform way, of course. So it's not just the number of words, it's entropy. And this is just the conditional mutual information given my representation, my compressed representation. So, and what this is telling us is that in language, the ratio of these two slopes, the slope of the tangent and the slope of the string, is a constant. This is precisely how power laws are defined, if you want. And in other words, I have some sort of a differential equation, if you want. Adding a little more complexity to my language is going to give me a little more accuracy in terms of specifying the topic, but not much more. how exactly, in a way which is proportional to the current, what I call efficiency of the language, which is how much mutual information is at a given complexity of the representation of the language. In other words, this is a nice law that I haven't seen anywhere else, and if it's true, it's nice. The meaningful information scales like some power of the entropy of the language. Which means language information about topics scales like an exponent of the representation of the word. This is actually a very simple relationship. Can we understand it? What does it say about language? So there's something very peculiar about it, because essentially this compressed representation, you can think about them as the statistics of words inside one of my clusters. So imagine, for example, that one of my clusters has to do, I don't know, with computer science. This has a very specific vocabulary with very funny, weird words that you know, computer science and never else. But still, if you're going to play this game of complexity accuracy relation for computer science papers, we're going to find the same exponent. That's exactly what it tells us. Now, if this is true, maybe we're talking about some universal phenomena here. I mean, this is something I didn't select computer science. The data selected for me. If computer science is indeed a natural subset of the language, then it must have the same behavior. How can this be explained? So essentially, that's what I said. Any subset of the language will have the same exponent. This is what it means. Now, remember, I'm talking about gross statistical behavior of language. What does it mean? Can it tell us something about the way words emerge, maybe? So here is a nice model, which I'm going to describe in a very sketchy way, because my time is up. But so, as I said, there is a differential equation which is related to this power law, which actually tells us, look, when you add a new word, you get a constant ratio in the efficiency. But this exponent has to do with how much of the information that of your investment in making a new word is actually useful. And this is a constant fraction. So now, when do we invent new words? I mean, essentially when we don't have any other choice. I mean, if you, no, my son just went to the army a year ago. Before that, he knew about 3 words about guns. After 1 month in the army, he had 200 words about guns. I mean, different parts and so on. Why? Because it costs him something not to know them, these words. I mean, essentially, it's really a problem of forcing to reduce your ambiguity. If you call this part in the wrong name, somebody may get hurt. So, in some sense, there is a power, a force that squeezes new words out of you in order to reduce ambiguity. So imagine this very simplistic, simple-minded approach. Words are generated at a constant average level of ambiguity. So I need to call this a dog and this a cat. Well, it makes sense, because if I call my dog a cat, it will get hurt, I don't know. Dog and cats not, but children, it might actually work like this. So you really want to know the names of people, because ambiguity has to be removed. So what I claim is actually very simple to show that this exponent has to do with the efficiency of words in a sense of the fraction of word entropy that is standing to meaningful information. And this is a constant. And this constant has to do with our tolerance of ambiguities in the language. If we have a constant tolerance of ambiguities, I'm willing to make 10% error, not more than that, then you're going to get powerless. It's as simple as that. Yes?
So if you were to look at a not a computer science paper, but a biochemistry paper, with all these very complicated terms that define a very specific, you wouldn't get this, I suppose.
I don't know. I have to see some details here. But I claim that this is true for language, and there's a good reason for that. I mean, so if language is generated on average, some of us are much more careful about ambiguities than others, of course, but on average, in some average usage of any population, we care about ambiguities in a constant rate. Then this constant rate is directly linked with this exponent, and it's going to explain it. Okay, so language appears to have a constant word efficiency, and this is a nice PowerPoint way of showing scaling. Essentially, if I blow up my statistics, and I look inside each of those small clusters, I see the same picture statistically again and again. That's what it means. Okay, so this is what I mean by scaling of meaningful information. And explanation. So of course, the natural explanation to this is to say power laws are too common to mean anything. the context of Zipf's law and other things that, especially things like fractal dimensions, I think they've been abused beyond reason in the literature. Some people even say never trust linear log plots. I mean, you get them too easily. Okay, this is one way of explaining it. Remember, notice that Zipf's law is not what we're talking about here. Those of you who want to ask this question immediately. Zipf's law is really something which has nothing to do with meaning. It has to do, monkeys typing or randoms typing on the keyboard will generate Zipf's law, because it has to do with essentially any process which has some constant probability of hitting the space will generate Zipf's law. It's any some process like this. So it's really not Zipf's law, because here I'm actually talking about scaling of information about the topic. It really captures the nature of meaningful. So okay, the other explanation, it's property of my analysis. It has nothing to do with language, it's the way you did your cluster. Okay, that's of course the natural, these are the referee reports that I should get, I guess. Here it comes exactly all the nice story I told you about information theory. It is model independent in a very profound sense. I didn't assume anything about the statistical data. This is the best, if I did it right, this is the best achievable ratio or achievable bound on compression versus meaningful information. If this is true, it's not a property of my analysis. Of course, it may be wrong. The other explanation, the last explanation, this is what I'm trying to suggest, is that this has to do with constant levels of ambiguity. And I don't want to, of course, in order to prove that, if this is true, I will need to do, and actually we are in the process of doing that, analyze many different corpora, for example. Analyze corpora in different languages. So I have some guy at Penn now who's doing analysis of Chinese based on the same concept. It's an entirely different structure of meaningful units that are no words anymore, that are more like the characters. Do I get the same kind of thing there? If this is true, then maybe this is really telling us something about the brain and not just a specific language of words. I don't know. Maybe. It's kind of prediction. Okay, now I don't have time to talk about all this part of the talk, but the whole thing can be extended. Let me jump from here to the conclusion. So this channel is perfectly matched to the source in a sense that I can achieve optimality without going to long blocks. It's interesting because this might tell us that the whole thing may actually be relevant for biological systems, if you're allowed to adapt the channels. Now, when we apply to large corpora of natural language, like this corpora of English, we observe empirically that this meaningful information, this complexity accuracy curve, looks like a power. What can it mean? And I suggest that it may have some cognitive meaning. And then the things I didn't have the time to talk about, I need 2 hours for that, is to talk about extensions to many more variables and some interesting relation to graphical meanings. That's for the next time. Now, I of course need to thank some of my collaborators without whom this can never happen. So, of course, Fernando Carrera is my host at Penn right now, and actually has been with me along this right from the very beginning when we started to talk about verb-noun clustering. And then Bill Bialik, who really was extremely helpful in formulating some of the mathematical ideas about information. And Neil Friedman, whose contribution was mainly in the third part that I didn't mention here, and in many applications that we do now to computational biology, the gene expression data and all other things that are interesting. And of course, many good students who helped me thinking and formulating, and especially doing the work, and Noam Slonim, Gal Chechik, Amir Globusoman, Bachach, Amir Levot, and Ilya Nemerman. At least 3 or 4 of those already have PhD theses that you can grab from the web page. Gal essentially helped in some extensions of this to in the context of irrelevant information and some attempts to apply it to the neural systems which didn't quite work out. And of course, Shannon. Thank you.
So, first, a comment, which is that if you go back and read Bar Hillel and these descriptions back in the linguists and the information theorists, he was very strict about the idea that you have to make a distinction between sort of quantity of information and the content of the information. This seems like a marvelous step in the direction of actually starting to look at it.
Yeah.
I have a question. Linguists make a distinction when they talk about ambiguity between, you can think of them as fine-grained distinctions versus coarse-grained distinctions, polysemy versus homonymy. So the bank for the organization versus the building would be a fine-grained distinction, but bank, the river bank versus the financial institution would be a large-scale distinction. And I'm curious what predictions you would make about the continuity of the kinds of distinctions you would get. And the reason I ask is that there's some recent evidence that cognitively there actually is a distinction between polysemy and homonymy. It's not just a continuous scale. So I'm curious if that, if you've done
it's
that.
a marvelous question. I wish I could answer it right now. But
I mean, would you predict a sort of continuous, I mean, the picture that you draw seems to predict some kind of sort of continuous scale.
It seems to there's some sort of self-similar, it's the same nature on all scales. You're saying that there's some sort of dichotomy, at least between, okay.
Well, I think you don't
I have to
predict
see the
polysemy at
evidence
all.
and think about it.
I think you don't predict polysemy at all. So you would expect that if you have a word which is ambiguous, it's ambiguous in a way which collapses distinctions that matter as little as possible for predicting what you really want to know. And so the fact that there is a sense of two meanings of bank, river bank and financial bank, which have nothing at all to do with one another, isn't the optimal way of coding the underlying concepts into words. So if I understand your picture right, it's that the words that we actually use are just they throw away some information about the underlying concepts, and if you do more clustering, you can throw away further information, but our language only gives us down to the word level. Maybe if you modify the words, you're splitting those senses further. But the fact that there's polysemy is sort of mysterious, and maybe it's a historical accident.
It seems like it would have to be deeper than that, because it seems as if there really is that same sort of trade-off at the level of senses as there is.
It seems that
words.
my analysis is too coarse-grained, to actually capture this. But I really have to see some statistical or some hard evidence. What is it that you're talking about? What are the quantities that are involved? Obviously, I'm averaging over many things here. So fine details, especially those type of details that linguists really like, beating one sentence to death. This is something that we have never
And
seen.
nothing in principle suggests that basic units have to be words per se,
Right.
at all as the student of PEM is looking at them.
That's right. More questions?
Almost hesitant to ask this because I'm not asking about something related to Zipf's law, but so words aren't generated by documents. I mean, words are generated by sentences, so they play a role in the sentence. So one of the role of a word is not just to convey information about the document, but also to say what word is going to come next. One explanation that you didn't put up on your possible list of causes for the constant is the rate at which information can be added within the words inside a sentence. I mean, words play an additional role other than just conveying information about the document. Could that be a source?
Well, one thing I didn't mention but was quite obvious from my analysis. This is a kind of what we call bag of words model. So I check the document well before I sample the words and all the connections, the inner sentence connection are completely lost. They don't reflect in any way in this statistic. So I can't believe that this can explain what I see. On the other hand, we know that any attempt to actually use the syntax and the short-term front-range correlation between words for actually doing a topic identification don't add too much, surprisingly.
No, I believe that, but well.
So the phenomenon you're talking about may be very interesting, but I threw it out of the way before I started. In some sense, this is statistics of just counting words in topic. That's it. It's a very simple minded. There's no structure whatsoever in this statistic, so I don't believe this can explain it. But it actually suggests some other experiments that can take this into account. And there's a lot more to be done. Yes?
So early on, you showed this grid of documents versus words. And
any of those numbers seriously, but they are empirical counts. Right?
Yeah, so they're not the true probabilities, in other words,
Sure.
which is what you'd really like in order to do that. What can you say about the case where your particular rows or particular columns are badly undersampled, or perhaps not even sampled at all? So you'd like to be able to generalize to words that you don't know about, that you've never seen before, but where you might have some external information that you'd like to somehow embed into the problem. I mean, I'm really asking two questions, I guess. One is about undersampling, and the other is about how to bring other information about the documents or about the words into the problem.
All right, good.
And these are questions that I've
Two very good questions. So let me, the undersampling, of course, it's a critical question, and I was trying to wash it out of the way right at the beginning, but obviously you can't trust anything in these curves at the very top, because you're overfitting horrendously. But it doesn't affect too much most of the story. And a better question, a better answer to this is there are actually many ways of smoothing. In particular, there's one that I like very much, which is using what I call the minimum information method. So essentially, given some sort of observations, among two variables, let's say conditional correlation or things like this, you can plug into this principle instead of the empirical distribution, which is, as you said, very noisy, something else which is a smooth version of which, but a very specific smoothing, which is take the one which minimizes the information subject to what you know about the two variables. This is something which we have been working together with Mary Globison recently, very in great detail, and we have nice algorithms. This is some sort of a generalization, maybe even a replacement for the maximum entropy way of smoothing things. Maximum entropy is based on precisely that. When you're given some partial observations, very sparse correlation or expected values, and you want a smooth distribution, and you take the one with maximum entropy because this is, in a sense, the least committed or whatever, least bias that you can. While the maximum entropy principle has all sorts of, you can argue against it because it's based on some assumptions about equally probable microscopic events or something like this. The minimum information is not. It's really minimizing, taking the one, what is it that I know about my relationship between X and Y, which is truly information in the data, take the one, the distribution which minimizes information subject to that. This turned out to eliminate many of the overfitting problems that I'm in. It actually, of course, gives me less information that I can actually get with the true distribution. There's no replacement to the real thing, but it eliminates some of the overfitting. Another way is, of course, to calculate the point where the separation of the empirical and the true things. So this is some sort of a, sample complexity analysis, very much in the spirit of learning of sample complexity analysis in learning theory. You can actually estimate the deviations. You can get some bounds and take the. This can be done. As I said, this all has an effect on only the top fraction of my curve, which you hardly see in what I showed you. So it's not going to change the exponent much. And I just know that I expect more error there. The other question, was it
right. So if you want to take some external information into account,
yes,
which will help you do generalization. So when you're talking about smoothing, you're saying your only information is that table of numbers.
No. But you're absolutely right that you can make predictions. Actually, Fernando and Lillian Lee and others have been playing with this quite a lot. You can use those things to make predictions about words and topics you haven't seen together in your data, or you haven't seen at all. If you let's say you see new words, all you have to know something about the co-occurrence of this word with some verb that you have seen.
Oh, no, I'm sorry, that's not quite the question. So suppose you have never seen before the word, you've never seen, you've seen some word X, but you've never seen the plural form, X's.
Oh, that's a morphology issue.
Well, I understand, but you'd like to be able to generalize from X to X's based on the fact that you know about Y and Y.
Absolutely, that's beyond the scope of what I'm trying to say here. This is really, it's very important. It's all this stemming and morphology questions. This is something which I completely suppressed here. It's very important. It can be done. This is not. It's an engineering issue. It's a very important engineering issue. But believe me that this can be handled. I I thought you were asking something about generalization beyond your training data, and that's an interesting question, which has a lot to do with how do you fill the holes in the matrix in some interesting way. Good Turing and other things like this.
And we have time for maybe one more very short question. If there is one, and if not, then we should let Tali catch his train. Thank you again very much.